So now let's look at a general Born-Haber cycle. What does a general Born-Haber cycle look like? Well, a general Born-Haber cycle starts off with, and this is true for any example, and we'll see some more right now, having earlier seen NaCls. It starts off from metal and non-metal. Then what you do is stage one is focus on the metal first. So you first atomize the metal, make it into a gaseous atom, then make it into a positive ion, so which means atomization of the metal and then ionization energy of the metal. Once that's done, then you atomize the non-metal and then you make that into a negative ion. And at that stage, you have your positive and negative ion, and then they combine with lattice enthalpy to make the ionic compound. And the overall reaction is starting from the start and ending at the ionic compound. And what we're going to do is we're going to take a look at some other examples I've given in my notes that have to do with some more Born-Haber cycles. So earlier we had seen sodium chloride, and we'll take a look at more complicated ones also. But first one we look at is as simple as sodium chloride, because we want to use a 1 plus and 1 minus ion, right? So we look at example of LIF. So the idea is that let's use the Born-Haber cycle to calculate the lattice enthalpy of LIF. What do I need? Remember, what information do I need? That's very, very important. You see, this is all the data you need to find this. You need formation information, you need atomization of the metal and ionization energy of the metal, which is many times given in the data booklet. Then you want the atomization of the non-metal, which is sometimes given, sometimes they give bond energies. So if you're given bond energies, we have to convert them into atomizations, something that we saw in AS also. Then we also have to give an electron affinity of the non-metal. Once we have all of that, we can find this. So in the example of LIF, if I focus on my metal first, C is the information for the overall compound given. Well, the enthalpy change of formation of the overall compound is given. That's great. Now, as far as the metal is concerned, have they given the atomization of the metal? Yes, they have right here. So that's the atomization of the metal. And they have also given the ionization of the metal. So that's also given to us. Then we go to the non-metal, because we need the non-metal also. Have they given the atomization of the non-metal? Not directly. They have given us the bond energy. So we're going to use this to find the atomization. But they have also given us the electron affinity. That's all right. So we have almost all the data. What we don't have is atomization directly. And what we need to realize is that bond energy for fluorine represents F2 becoming 2F. And that is delta H of 158. And remember that for gaseous molecules, half of its bond energy is atomization, because bond energy is for 1 mole of gaseous atoms, while bond energy is for 1 mole of gaseous atoms, while atomization is for 1 mole of gaseous atoms. So bond energy is for 1 mole of gaseous molecules, while atomization is for 1 mole of gaseous atoms, and many times atomization will be half of the bond energy. So it'll be half of 158. In this case, that comes out to, I believe, 79 kilojoules per mole. So they didn't give you atomization of fluorine, but you found it. And you save that. So we do the math beforehand and save it. So instead of using bond energy, we have converted that into atomization, and now I can use that ahead. And what do I use it for? Well, we use all of this to plug it into a Born-Haber cycle, which includes what? Metal atomizing, ionizing, non-metal atomizing, electron affinity, combining them into lattice energy to form the whole cycle. Now your slides also have the whole diagram, but I want to paste that diagram here, and so we can take a look at it. If you guys give me a second. So if I put this all in a Hess cycle, this is what the Hess cycle would look like. Basically, you're starting from right here. So I'm going to mark that so that's easier to find. So the green highlighted region is your starting stage. Your metal and non-metal in a standard state. Step 1 and 2 is atomization of the metal, and then ionization of the metal. And then step 3 is atomization of the non-metal, and then electron affinity of the non-metal. And then this is lattice enthalpy. And now when you do more of this, you don't always have to draw the Born-Haber cycle, but when they ask to draw it, And sometimes they do draw it for you and even ask you to identify the steps, then you should draw it. So in the next few questions, you will be drawing Born-Haber cycles. But the idea is that it's pretty straightforward. In step 1, you'll have the atomization of the metal, which is lithium. Step 2 would have the ionization energy of lithium. Step 3 would be the atomization of fluorine. Step 4 would be the delta H electron affinity of fluorine. And step 5 is the lattice energy, which is what we have to find. And step 6 is delta HF. And also, simply speaking, if the graph is drawn for you, the Born-Haber cycle, all you gotta do is just put values in these arrows. Now these arrows are also, by the way, drawn to scale, so some are larger than others because they try to make them as scalable, like the larger arrow for a larger value. We don't have to worry about that for ourselves, but it's nice to see that in the books. For example, so if I'm filling out this out, step 1 would be plus 161. Step 2 is plus 520. I'm looking from the data in the question. This is the atomization of lithium, ionization energy of lithium. Step 3 is the atomization of fluorine, which is literally half of 158, which is 79. This value. And then the electron affinity of fluorine is minus 328. And then the delta lattice energy is unknown to us as X, and the formation is minus 617. Yeah. And so you can use, so basically what are we finding? We find the lattice energy, which will be plus 161 plus 520. Then the fluorine is plus 79. Then plus minus 328. Then plus X. All of that equals to the overall value of minus 617. And you can solve for X this way. Yeah. Which, by the way, should come out to minus 1049 kilojoules per mole. Yeah.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
So now this is basically how you solve questions on Born-Haber cycle. Now this is, by the way, definitely going to be the easiest chapter in the whole of A-level chemistry. The only place people make a mistake is that when the compounds are not straightforward as NaCl or LiF, when they have more than one ion for an element, like example being here of MgCl2. Now MgCl2 is a compound where magnesium becomes a 2+ ion, while you need 2 chlorines to become 2 chloride ions. So basically the first thing you'll recognize is that you're going to have first and second ionization energies of magnesium, which are given to you here, but in exam papers they'll be given to you explicitly in the data booklet, not in the question. So for a metal, I have the atomization of the metal and the ionization energies of the metal. For the non-metal, they have given me the atomization of chlorine, but I got to remember I'm going to use 2 atoms of chlorine because I've got to make MgCl2. And I don't need second electron affinity because that's a 2- ion. This only makes a 1- ion. So I only need the first electron affinity of chlorine. And they have the standard enthalpy of formation of MgCl2. So the only difference here would be that first difference will be that you'll have to cater to magnesium's second ionization energy. And the second thing you'll need to worry about is the fact that you need 2 chlorines throughout. Because if you think about MgCl2, it needs 2 chlorines. So you got to keep that in mind also. So the already drawn Born-Haber cycle in the examples in your notes, I'll just focus on that. I'll skip the data. We already have all the data. And if I look at the Born-Haber cycle, and I'll focus on this right here in the dead center, is I'll highlight the starting point first, which, by the way, is right there. You're starting off from magnesium and Cl2, not half Cl2. Half Cl2 will give you 1 chlorine atom. Cl2 will give you 2 chlorine atoms. So first look at the pinks. The pinks may magnesium becomes a gaseous atom, and then the first 1+ ion and then a 2+ ion. At that stage, is the atomization of magnesium, ionization energy of magnesium, second ionization energy of magnesium. Then you have Cl2, which means both Cl2s have to become gaseous atoms, which would mean that is twice the atomization of chlorine. Understand? Because you need 2 Cl atoms. And then you have 2 Cl minus ions. And that's where people miss this out. This is where I'm going to highlight this. That each Cl atom becoming Cl minus ion is 1 delta H, Ea. But here there are 2. So this is 2 times. So things to worry about is right here. 2 times. This is where people make a mistake. It's twice the atomization and twice the electron affinity. And then you have lattice energy. And that's literally what you do. So if I'm looking at the values, there's values for the first atomization of magnesium is 148. You know. First ionization energy of magnesium is 736. Second ionization energy is 1450. And each atomization of chlorine is 122. So it'll be 2 times 122. And this will be twice the electron affinity of chlorine, which is 2 times minus 349. And that is unknown, while my delta H is minus 641. So here the math comes out to be what? It's 148. I mean, if I just were to, zoom out just a little bit and write it here. So it'll be 148 plus 736 plus 1450. That's the metal. And then the non-metal will be 2 times 122 and 2 times minus 349. But lattice energy is just X. It's not 2 times, because it's making 1 mole of the compound. And all of this will equal to minus 641. And then you calculate the value for X. See how big the value is in this case. Minus 2521 kilojoules per mole. And this, even though this has very exothermic, it also has a high endothermic side, because it has first and second ionization energy. So that's the kind of things you have to also focus on. Understand the Born-Haber cycle tells you how big the endo parts are and how big the exo parts are. And in this case, that comes out to minus 2521. All right. So the last example I want to go over in this case, because in this example that I showed you, the anion was twice. Now I'm going to show you where the cation is twice. And the reason for that is that the cation is a 1 plus ion and the anion is a 2 minus ion. And the reason why I want to do this example is because now you will be dealing with second electron affinity also, because that's how you make a 2 minus ion. So and look at sodium, you've given the atomization of sodium and the ionization of sodium, the first ion, because 1 plus makes only 1. But obviously remember, in the Born-Haber cycle you'll have to use 2 sodiums. So you'll have to atomize 2 sodiums and ionize, because the lattice energy is simply 2 sodiums and 1 oxide ion becoming Na2O. That is the lattice energy reaction of Na2O. 2 sodium ions and 1 oxide ion becoming Na2O. So I got that. So now for the non-metal, I've got the atomization of oxygen. Perfect. I've got the first electron affinity and the second electron affinity. If I'm given bond energies and not atomization, I will divide the bond energy by 2 to get the atomization before I start the question. That's the key. All right, always remember that. And the Born-Haber cycle for this Na2O, which I'll just show you right now. But before I show you the Born-Haber cycle, one thing I want to highlight using the previous question is that you can also combine ionization energies. Like in the previous example, if you go back here for a second, just for a second, you notice that this arrow was the first ionization energy of magnesium and this was the second ionization energy of magnesium. You can also give one overall arrow to go from magnesium to magnesium 2 plus, and that arrow would be the sum of first and second ionization energies. Makes it a little more simpler to draw. So why am I saying this? Because in the example I'm showing you here for sodium oxide, we've got the first and the second electron affinity of oxygen. But if you remember earlier, we had discussed that I can combine them both into a reaction where O gains 2 electrons to become O2 minus. And that delta H would be the sum of Ea1 plus Ea2. Yeah. So Meaning, in the Born-Haber cycle I'm about to show you, instead of doing it in 2 steps of 1 minus and then 2 minus, we can do it in 1 step and combine these two. If I combine these two, what do these values come out to be? Minus 141 and 798 becomes how much? 657 positive. Yeah. So the Born-Haber cycle has that here. This is the Born-Haber cycle. Where do I start from? I'm starting from right there. Sodium and oxygen. Now I need 2 sodiums and half oxygen molecule. Why half? Half O2 gives me 1 O. And 2 NAs give me Na2. So 2 NAs become 2 Na gas, which is 2 times the atomization. Then we have the ionization of magnesium, but 2 moles are being ionized. So 2 times 496, I believe. And then this is the atomization of 1 oxygen right here, 249. Then this arrow right here that I'm pointing to is your sum of first and second. Remember, minus 141 and then 798 gets you this. And then they all combine to make one large drop in lattice energy to become sodium oxide. So in this particular case, it would be 2 times, remember 214, which is 2 times. If I were to go by the actual values, not multiply them, remember 214 is 2 times 107. 992 is 2 times 496. So it's 2 times 107 plus 2 times 496. I've taken this from a book, so they've multiplied it. I like them as raw data, so it's easier to see, oh, there are 2 of them, there are 2 of them. And then oxygen is 249, and the sum of first and second ionized electron affinities are minus 141 and 798. And that plus x equals to minus 414. And when you do all of this math, the x comes out to minus 2526 kilojoules per mole. And so Born-Haber cycles can be drawn for any ionic compound for us to find the lattice enthalpies. And we'll discuss the lattice enthalpy and its usage in other predictions later. But first, we are trying to draw how to find the values for lattice enthalpies. And those are found using Born-Haber cycles. And this was another example of a Born-Haber cycle. Yeah. Now, having seen these examples, what I'd love to do is have you guys try this out, where you're using a Born-Haber cycle, draw a Born-Haber cycle, draw the whole thing, and find the lattice enthalpy of calcium fluoride, which is CaF2, which will involve the first and second ionization energies of calcium and 2 fluorines atoms, atomization of fluorine and electron affinity of fluorine times 2 each, and draw that whole thing out to find the lattice enthalpy of calcium fluoride.
Hey there! If you found this A-level chemistry lesson helpful, why don't you head over to our website, altacademy.org, where you can sign up for the full A-level chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for?